So let's do part two of this lecture on Maxwell's equations. Last time we left off with the understanding that the four-vector current density is conserved, and we wrote down that equation. So we begin with the bit of Maxwell's equations that we understand, and that's Gauss's law, right? That the divergence of the electric field is proportional to the charge density. Okay, point by point. It's a local expression, and we hypothesize that it's true at every space-time point in the Minkowski diagram. Okay. So the claim is it's true for any charge density. It's an equality at R and T. I don't need to know what's happening before or later or to the left or to the right. It's an equality at a particular point, and so it's sensible to hypothesize that it holds over all of Minkowski space for every charge density. It's just the idea that charge density generates the electric field at that point. That's the only way to make an electric field at that point, is with a charge density at that point. Okay, the simplicity of it is part of its strength. And we're going to come back to it because that simplicity is going to get us simplicity elsewhere throughout the discussion of Maxwell's equations in places where perhaps it's not so obvious. Okay, but we'll derive it using the principles of relativity. So that's what I want to do. I've been saying, well, this equation should be covariant, blah, blah, blah. Let's put that to the test. So let's suppose that this is true in the frame S prime, and let's see that it's true in another frame. I'll call it S. See, this is very puzzling. You look at this equation. Does this look like a covariant equation to you? Not to me. It's a three divergence. There's no space-time symmetry there. How can that equation be covariant? It's a little bit peculiar. Well, it can be covariant because it's a local equation. You know, it states the divergence of E is equal to rho at that point. But it's challenging nonetheless, and let's work it out. Okay, let's work it out. Does this equation hold in S if it holds in S prime? Okay, so let's just work it out. So now, you know, the traditional thing in introductory relativity courses is to boost charges, boost particles, you know, perhaps boost the electric field. It's more sophisticated, but we've done it. But now we're going to go to the fundamentals. We're going to boost differential equations, okay, to find out the set of differential equations that's truly covariant. These equations are going to be local equations, okay, so they're causal and they can be fundamental. But our attitude is much more sophisticated now, okay. It's something a lot of textbook writers forget, okay. What's underlying Maxwell's equations and the equations of relativity are local differential equations. Those are the objects you want to study, and we want to see how they boost, to check that they're covariant and to understand what that implies. Okay, this is the way to get at the fundamentals of Maxwell's equations. Okay, so let's do it. Okay, so here I've written down the Maxwell law. I've written down the components of the gradient prime is d by dx prime, d by dy prime. I've written out the divergence, that's equal to rho prime. And I know how every bit of that equation transforms from one frame to the other. How does dx prime transform? Well, it's a bit of a Lorentz transformation. I've written it down here. How does the electric field in the x direction transform? Well, I just look back at our discussion of the transformation properties for E and B, and I recall that it's unchanged. I've written it down here. And then similarly, I know how to transform d by dy prime, that's d by dy. I have to transform the electric field in the y direction, and I look back and I see that that transforms according to a simple formula that's reminiscent of a Lorentz transformation for space and time, but has different details. Okay, and I wrote that in. I do the same thing for my z component over here. That's easy. And then I do on the right-hand side, I transform my rho prime from one frame to another. It gets contributions from rho in the other frame, and the current density in that direction. Okay, so oh God, that's complicated. Let's see. I have two kinds of terms. I have terms which are proportional to gamma, and I have terms that are proportional to gamma v. Gamma v. Gamma v. Okay, v is arbitrary. That's the velocity between the two frames, s and s prime. This thing has to be covariant for any inertial frame. So that's it. So v is arbitrary. Okay, so we could collect all the terms that are proportional to gamma. What are they? Here's gamma d by dx of ex. Here's gamma d by dy of ey. Here's gamma of d by dez dz. That's just a divergence in the other frame. So that's one contribution to the terms that go like gamma. Anything else that goes like gamma, and only gamma, not gamma v? Here it is, the charge density, gamma. Okay, so I push that. That makes up one term. And there I see, if that term happened to be 0, it's Gauss's law in the other frame. Great. But what's about all these terms that go like v? So I collect them. So I pull out v gamma, and what do I see? Okay, well, I see various terms. I see the time derivative of ex. I've written that down here. Okay, and then I see d by bz by dx, and minus, different sign, d by dby by dz, and I've written those down here. And then on the other side of the equation, I see a minus j sub x, so I throw that onto the left side of the equation and get rid of that sign. Okay, so now I recognize that v is an independent parameter. Okay, so both of those expressions in parentheses have to independently be 0, and for the right-hand side to be 0. For example, I can take gamma, it's a expression greater than 1. I can divide it out, and then I have a quantity here that has no v in front of it, and here I have a quantity with v in front of it. V could be 1, 2, 3, whatever. So to get this that sum to be 0, it has to be that the point in parenthesis must be 0, independent of the other part, and this must be 0, independent of the other part. Well, let's take a look at this at this equation. I see here E in the x direction, I see J in the x direction, and then I see this collection of terms involving the rate at which the magnetic field, different components of it, vary in x, y, and z. But I look at that, that's the curl of B in the x direction. So I've gotten one component, the x component of an equation, and if I made boosts in the y and z direction, I just generate the other components of this equation. Right? My world, it has rotational symmetry, so I know if I get one component of a vector equation, I'll get the others just by changing the direction of the boost, and you can check that. Okay, but anyway, we can write this fellow down, okay, because here I made the identification of the tricky part here, that this collection of derivatives of the B field is just the curl of the B field in the x direction. So I'll write it down then now, and we'll write it down for all three components as a vector equation. It says that the curl of B is equal to 4 pi k over c squared times the current density plus 1 over c squared dE by dt. And we recognize that. That's the Maxwell-Ampere equation. Okay, there are three components of it. Okay, and the great thing we've done here is that we predicted what's called a displacement current. You know, if we don't have that term here, you look at that and you say, oh, that's Ampere's law. Okay, and remember, Ampere's law holds for stationary currents. Okay, but it's not not correct in general. If you have strong time dependence in a problem, then there's another term, okay, and it's the displacement current. It's a very awkward thing to discuss in a conventional textbook on electromagnetism, okay? They go nuts about this term. Well, it comes from special relativity, and we get it for free. Okay, we get the full time-space equations of Maxwell, and we have to get them because we're insisting on covariance. Okay, so I write it down like that, and that's a triumph. Okay, we started with Gauss's law and some general principles. We put them together. And now we know, yes, Gauss's law is covariant, but if Gauss's law is going to be true in all frames as a local differential equation, something else has to be true as well, and that's Maxwell-Ampere's equation. Okay, these equations are tied at the hip. Okay, for example, I can go back to this derivation, and why don't I let v here be infinitesimal? If it's infinitesimal, then I'm back to the original frame I started with, in which I hypothesized the existence of a general covariant form of Gauss's law. Back to frame S, where I hypothesized Gauss's law, and I see, oh, there's something else going on. I didn't know it, but the Maxwell-Ampere's law was also true there, right? Because if you take V very small, you're back to that frame. I didn't know yet how to calculate how currents generate B fields. Okay, I didn't know that. I could think about Gauss's law because it's so simple. Okay, but I learned in order for Gauss's law to be true, the Maxwell-Ampere's law has got to be true as well. Okay, how smart is this equation? Well, it's really smart. It knows current conservation. Let's prove that from this equation, with the displacement current, we have current conservation, right? Okay, because here's J. What I want to do is to get divergence of J. So I'll take the divergence of the Maxwell-Ampere equation, okay, and then what do I get here? On the left-hand side, I get divergence of a curl. You know from your vector calculus that's 0, or for any adequately smooth vector field, that's 0. So on the right-hand side, I have divergence of J, and on the right-hand side, I have divergence of this expression. Well, so I can interchange the d by dt with taking the divergence to get the divergence of E here. But the divergence of E is what? It's 4 pi k rho. Okay, so on the right-hand side, I just got divergence of J and the time derivative of rho. The prefactors are common, and they cancel out, and I'm left with current conservation, right? So current conservation is built in to Maxwell's law. It's a consequence of it, as we see in this example. Okay. And so now I have a little bit more work to do. Okay, that gives me 4 of Maxwell's equations. They're what's called the inhomogeneous equations. They're the ones that involve the charge density and the current density. Well, there were more of Maxwell's equations. I got these Maxwell equations from Gauss's law for the electric field. I can also write down Gauss's law for the magnetic field. What is the divergence of the magnetic field? Well, it's going to be proportional to the density of magnetic monopoles, okay, sources of the B field. Well, last time I looked, nobody had found a magnetic monopole, and so the density of magnetic monopoles is 0. And so this is just the experimental statement that nobody's found a magnetic charge. Rho sub m is equal to 0. Rho sub magnetic is equal to 0. Okay, and that's this local statement of the absence of monopoles, and I take that as one of the, and that's okay, and that's a statement. Okay, and that's an equation. It's a local equation. Okay, so why don't we play our game with it and require that this equation, a kind of special case of Gauss's law, is true in every frame. Well, that's easy for us to do. We know exactly how that's going to work. I'm going to write this equation out in the frame S prime, and then I'm going to, everywhere I see d by dx prime, I'm going to just relate it to d by dx and d by dt. I'll just boost it. Everything boosts. I know how the magnetic fields boost. I know how the gradients boost. I write it all out. Okay, I play my same game. I collect those terms that go like gamma. I collect those terms that go like gamma v. Okay, just like before. The term that goes, the parentheses that goes, that's associated with gamma is I see just the divergence of d, and so I see that statement, that local conservation law, that local statement of a Gauss's law for monopoles, magnetic monopoles, is true in every frame if it's true in any one. And then I look at this other term, okay? It involves, let's see, let's collect the v terms. V terms. It has a time derivative of v in the x direction. I've written that down here. And then it has some other terms here, which is d by dy of e sub z, and then minus d by dz of e sub y. Aha! That collection of terms I recognize as the x component of the curl of E, similar to the previous page. Okay, and so I see again one component of a vector equation, and I write it down as a full vector equation. It tells me that the curl of E is minus dB dt, point by point in space-time. I recognize that. That's Faraday's law, right? A time-changing magnetic field generates an electromotive force. You've probably written it down as an integral expression, and then in passing you notice that this was the underlying equation. For us, this is the equation, okay, the fundamental equation, and we can apply it to particular geometries and get the other expression that you might be more familiar with in applying Faraday's law to electromotive circuits and devices and moving magnets. Okay. Okay. And these are the four sourceless magnetic Maxwell's equations. So in summary, okay. So in summary, we have all 8 of Maxwell's equations written in Cartesian coordinate. We have Gauss's law, Ampere-Maxwell's law. Okay. We have the statement of no monopoles, and we have Faraday's law. Okay. Okay, and they're all related. Over here, you see for the inhomogeneous equations, we have one equation for each component of the current density: rho, Jx, Jy, and Jz. Okay. We know that under boost, rho mixes with all the different components of J, and so the right-hand side will mix. And in any particular frame, you'll find a linear combination of Gauss's law and the Ampere-Maxwell's law. And similar, but a little bit more simple in the other case where there's no source. Because why no source? Well, there was no magnetic monopoles around. So that was clearly the case to write this one down. And then we get the big surprise, okay, that Faraday's that we have Faraday's law as written down there, and looks as though I really should complete it. Sorry. Okay. Okay. So what do we learn from all of this? We see that Gauss's law and Ampere's law comprise a quartet, the 4 components of a 4 vector. They mix on the boosts. Okay. From group theory, we have a 4-dimensional representation of the Lorentz group, right? The right-hand side is just a 4 vector. If 1 was missing, we would fill its slots using a symmetry operation. Right? That's what we've managed to accomplish here. We've taken one of the slots in the quartet, okay, which was Gauss's law, and then we boosted it. We made a symmetry operation, and then we filled in the other slots. And the other slots were the 3 components of the Ampere-Maxwell's law. So it is, in that sense, a group theory problem. And we've discussed that in the recitation section. Okay. You guys forced me to talk about representations of the Lorentz group and a group, and then the generators of the group, and the algebra of the group, right? And in that recitation section, we related the generators of the group to Maxwell's equations. Oh, so that was fun, but we're not going to do that here because you're not bossing me around here. Okay. Okay. But it's like a symmetry operation. When you study quantum mechanics, right, and you're looking at the multiplets of different angular momentum, then you know to get from one multiplet to another, you have raising and lowering operations. Okay, if you give me the S wave, for example, well, the J equals the J sub z equals 0 state of a multiplet, say J is equal to 2, then I can do raising, lowering operations and get you the wave functions for all the other members of the multiplet. I'm doing a symmetry operation on a simple state and generating more complicated states. That's generally the structure of the argument we made here. It's just hidden because we're boosting and we're doing differential equations, but it's the same idea. In elementary particles, remember, you had the eightfold way as a symmetry of strong interactions, a broken symmetry, okay? And then experiment would complete those multiplets, and maybe there might be one missing, the famous omega. A baryon was found that way. It was missing. You knew where to look for it. Its energy should be related to the other members of the multiplet. You made an experiment, and you looked for it, and you found it. You're completing the representation of a multiplet, of a representation of, in that case, a broken symmetry called the eightfold way. So that's one example, and it's a general principle of doing group theory, and we've had some fun with it in recitation. Okay, second lesson learned, equations are first order partial differential equations, and they only involve J mu. They are local. Okay, some textbooks writers are a little bit confused about this point. They can't really defend the fact that the Maxwell's equations only involve the 4-vector current density. Okay, that's a very simple property of the full ensemble of moving charges. There are other features of the moving charges, and they don't enter into Maxwell's equations. That's because Maxwell equations are local differential equations. And remember, if you ever get confused about that, just go back to one of the equations, which is Gauss's law. Gauss's law tells you simply that the source of the electric field, divergence of E, is equal to something. It's equal to the charge density, okay? And that's very simple to think about. Only charge densities generate electric fields. Okay, so if you're comfortable with that, then the other aspect, okay, Ampere-Maxwell's law follows by a symmetry operation. Okay, and so J is sufficient to know to write down the fundamental equations of Maxwell. These we'll see in the next lecture. These imply the wave equation for light with a velocity that's equal to the speed limit. The electric and magnetic fields become dynamical fields. Instantaneous potentials are replaced by retarded propagators, and causality is built in to these equations from their local properties. So we'll be discussing that in more detail, and we'll look at the wave equation, okay, and the wave equation with sources that are more complicated, that do look at, are sensitive to other aspects of the collection of charges and currents that you might have in your space-time. Okay, but that's for next time.